Okay, so picking up at question 7 to do 7, 8 and 9 of the November 2017 Intermediate GCSE Maths Paper 1, Unit 1, Non-Calculator. Picking up at question 7, this is a proof question. So for a proof question, you've got to use the information that you're given to show without a shadow of a doubt that you know the fact or angle fact that you've been asked to prove. So I need to prove that I know APQ is an equilateral triangle. APQ is this little triangle down here in the corner. So what I'm aiming to show is that these three corners are all 60 without a shadow of a doubt, because then I would be dealing with an equilateral triangle. That's the maths identification, the maths properties of an equilateral triangle. So to start off with, I've got to work through the information that I'm given. I'm told that I'm dealing with a quadrilateral, so this tells me that my four corners of the quadrilateral add up to 180. So if I add together the three corners that I know, I'd have 122, 85 and 93, and if I add those up they come to 300. So take off 300, I got 60 left. So officially I'm going to put down here DAB is 60, and my reason is angles in a quadrilateral add to 360. I'm told up here as well, that I haven't used this, I'm going to use it now, that APQ is the same length as AQ. AP, sorry, is the same length as AQ. AP is this short side here, AQ is this short side here, and they are both part of the triangle I'm interested in. If a triangle has two sides the same length, it's an isosceles triangle, and it also has two angles that are the same size. So given AP equals AQ, triangle APQ, that's the name of it, is an isosceles triangle with two sides the same, which is why I know it's an isosceles, because AP is the same as AQ, and two angles the same size. And those two angles would be angle Q and angle P. So angle P and angle Q are identical. I haven't worked out what they are yet, but angle P and angle Q are identical. So I've proven that. I just need to prove how many degrees are in each corner. So angles in triangle APQ add to 180. That's a fact. So 180, take away angle A, take away that 60, leaves 120, and because it's an isosceles triangle, that 120 needs to be split equally between angle Q and angle P, because they are the same, which means I've then proven, without using the fact that it's an equilateral triangle, I've proven without a shadow of a doubt, so I use my little triangle to say, therefore, angle Q equals angle P, which equals angle A, angle, which equals 60 degrees, which implies triangle is equilateral, because any triangle with three sides are equal and the three angles are 60 degrees each must be an equilateral triangle. Question 8. Look at the following descriptions of special quadrilateral shapes. Circle the correct name for each one. we've got kite, rhombus, square, trapezium and rectangle. So some little sketches. A kite is basically like the kite you fly in the sky. A rhombus is a square that has fallen to its side. A square. A trapezium is a four-sided shape where the top and the bottom are parallel and the other two sides aren't. And a rectangle is a rectangle. Okay. So there's a little sketch of each one. I'll just pop the names underneath it so that you can remember them. Okay, so the sides of these would be pairing up and parallel and the same length, as would this pair, pairing up and parallel. They are related to each other. They just have 90-degree corners in a square, but you don't have them in a rhombus. A trapezium only has one pair of parallel sides. A kite doesn't have any parallel sides, but if drawn well, has symmetrical properties. Yeah, that'll do. And the rectangle, a bit like the square, we have right angles in our corners, parallel sides, but in pairs where the top and bottom would be the same length and the two sides would be the same length. Okay. Question A, its diagonals intersect at 90. Difficult to see. And only one diagonal is a line of symmetry. Difficult to see because of my bad drawing of a kite, but these diagonals here would intersect at 90. These diagonals here would, and likewise these diagonals here, they would. But where it says one diagonal is a line of symmetry, that's going to be only one diagonal is a line of symmetry. That's going to be that line of symmetry there. So for question A, it's going to be kite. Question B says only one pair of sides are parallel. So as you can see in my diagram underneath, the trapezium only has one pair of sides that are parallel. Kite doesn't have any, and then the other three both have two. And then for part C, all four sides are equal. Its diagonals are not equal in length. We're going to be talking about the rhombus. All four sides of the rhombus are equal, but this diagonal will be longer than the other one. So that's why it can't be the square. Okay. Question 9. We're going to fill in this table, and we're doing it without a calculator, and then in part B we've got to actually draw that quadratic graph, and then in part C we've just got to answer a general fact. First of all, I know that if I have an equation that's got an x squared in it, the general shape of this graph is going to be a U shape or an N shape if it's got a minus x squared in it. So I know my graph is going to look like this. Okay, I've only got one coordinate to find. It had to be one with a negative number, but I've only got one coordinate to find. So I know that the majority of those 4 marks is going to come from drawing the thing. And I can get those points even if I don't work out the coordinate that's missing from the table. So don't walk away, make sure you've tried at least finding the coordinate and then plotting all of the other points and joining up your curve as best you can. So I need to work out the value of 2 multiply my number squared, take away 5, and my number is minus 1. Minus 1 squared is the same as minus 1 times minus 1, and a minus times a minus makes a positive. 1 times 1 is 1. So minus 1 squared is actually worth just a normal 1. So that's 2 times a normal 1. Take away 5. 2 times 1 is 2. Take away 5 equals 3. Pardon me for coughing. Minus 3. 2 take away 5. Minus 3. Now that I've got that in my table, I'm ready to do the plotting. But I've noticed that on this vertical axis here, there aren't any numbers. So I've got to put the numbers in myself, making sure that I use a scale that's going to allow me to go from my y values all the way up to 13 and all the way down to minus 5. So marks for plotting. If I've got to want to go all the way up to 13 and all the way down to minus 5, I'm thinking, I'm going to check before I actually do this though, so I'm thinking 5, 10, 15, 20, yeah, I'm thinking I'm going to count up in 5s. I just checked before I go ahead and draw it, so don't just start drawing until you've checked it's going to fit. So this point here is now going to be 5, 10, 15, and I don't need this for 20. And then below will be minus 5. Below that, minus 10. And I don't need to worry about it, but down there would have been minus 15. I know from the table that everything's going to fit on the graph now, so I'm just going to run through plotting the points. So for the first pair that I plot, I got to go across to minus 2 and up 3. I've just chosen a scale that means I'm jumping 2 squares at a time. So if you see here on the axis, I've zoomed in, if you like, and I've now got 1, 2, 3, 4, 5. Every 2 squares is a unit. So across to minus 2 and up 3 will actually be that point there. Across to minus 1 and down to minus 3. Plot it again. Across to 0 and down to minus 5. Across to 1 and down to minus 3. Across to 2 and up 3. And then the last one across to 3 and up 13. And that's the reason that I needed that scale, to make sure that that 13 would fit. Plotting the points isn't enough. You've got to make sure you've joined them together with a curved line. And you do have to make sure that your curved line goes through the point. You can't just randomly draw and miss the point like that, because that will lose you marks. Make sure you go through the point. So I'm not drawing this in one step. You'll notice that I've gone through it part by part, like a dot to dot. And it's to make sure that I've got contact at every one of those points, so that I can gain marks for accurately plotting. Okay, part B, I'm looking at a quadratic curve. I know I'm looking at a quadratic curve because all x squared curves are going to have that shape, and all minus x squared curves would have that shape. So I know, because that positive shape, that one's definitely ruled out. When I have a look then at the cut-in point of this graph and where it's cut in the axis, I can see that it doesn't go through 0, 0, it doesn't go through the origin. So it can't be the first one, because when x is 0, y would be 0. So that one's ruled out. I'm not going through a negative number, so I can't be taking away 3, or this would be as low as 3 down here. That only leaves me two options. But in that last question there, if I had 3 as a multiplier, then that would still go through the origin because it'd still go through 0, 0. When x was 0, y would just be 3 noughts. So that would have had to have gone through that origin as well. So this only leaves me one possibility. This plus 3 looks good because this is 3 or high enough to be 3 units up, and the shape of the graph is positive. So I think I've got it covered.